Welcome back to the deep dive. Usually when we talk about breaking news, it's about something loud. Politics, a big tech launch, something you can really see.
Yeah, something tangible.
Exactly. But today we're looking at something incredibly small that is making, well, a deafening amount of noise in the scientific community. We are talking about new physics.
It's a phrase, isn't it? It gets thrown around a lot, usually in science fiction, time travel or multiverses. But inside actual research labs, new physics is. Well, it's the Holy Grail.
It's the big one.
It's the moment we find out our map of reality is a huge blank spot on it.
And that map, for the last 50 years or so, has been the standard model. It's the fortress of physics, right? It explains pretty much everything.
It does, yeah. It explains how all the basic particles interact, how the fundamental forces work, and it has stood up to, almost every single test we've thrown at it. It's probably the most successful theory in history.
Right. If the standard model says a particle should zig, it zigs.
It zigs with terrifying accuracy. Almost always.
Almost always. And that's where this little guy comes in, the Kanon.
The Kanon, our little troublemaker.
I was reading through the notes on this, and the Kanon just feels like the punk rocker of the subatomic world. It's messy, it's unstable, and it just refuses to do what it's told.
That's a great way to put it.
And recently, it did something in an experiment that was so unexpected, it might have just put a crack in that fortress wall.
Oh, it's a significant crack.
Yeah.
This isn't a rounding error. We're talking about an experiment that produced a result that, statistically speaking, it just shouldn't exist.
We're going to get to the numbers, specifically this 0.25 versus 4 thing, which sounds more like a weird sports score. But before we do that, we need to meet the player. So what is a Kanon?
Okay, so to get technical for a second, a Kanon is a special type of particle called a meson.
Right.
And mesons are part of the larger family called hadrons.
Hadrons, like in the Large Hadron Collider. That's the family name.
Exactly. But what makes a Kagon, and really all mesons, so weird, is what they're made of. We're used to stable stuff, right? Protons, neutrons, they stick around. The Kagon is different. It's made of a quark and an antiquark.
Okay, see, that's where my brain starts to go a little sideways. I always thought that if you touch matter, like a quark, and antimatter, like an antiquark, they just annihilate.
They do.
In a big flash of energy. So how does this particle even exist?
That's the tragic beauty of it. They're bound together by the strong nuclear force, but it's a very volatile marriage. They aren't meant to last. They're born, they exist for a fraction of a microsecond, and then they decay.
And decay doesn't mean it just, rots. It means it transforms.
Yes, exactly. Think of it like a shapeshifter. The Kagon just falls apart into a spray of other lighter particles. Pions, muons, neutrinos, things like that.
And that's where the standard model comes in. It's like the traffic cop.
Perfect analogy. It tells the Kaon, okay, you can turn into route A, or route B, or route C, and here is exactly how often you're allowed to take each route.
So it sets the odds. The probabilities.
There's incredible precision. We've calculated these branching ratios, these probabilities, and we know that for every, say, billion kaons, a certain number should turn into this, and a certain number should turn into that.
So scientists are just counting, they know it's on the menu, and they're just checking how many times each dish gets ordered.
That's a huge part of particle physics, yes. You smash things together, create billions of kaons, and you count the debris. And if your count matches the prediction, the standard model wins again.
But in this experiment we're looking at, the KOTO experiment in Japan, the count was, well, it was off.
It was way, way off. They were looking for a very specific, ultra-rare way for the kaon to decay. This is like the golden ticket of decays. It's really hard to spot.
The notes said this decay is so rare that the standard model predicts it basically shouldn't even happen in a sample of this size.
Right, small in particle physics terms. Based on all their data, the standard model predicted they should see, get this, 0.25 events.
Okay, let's stop on that. 0.25. You can't have a quarter of an event. That means you expect to see nothing.
It's a statistical average, yeah. It means if you ran this exact same experiment 4 times in a row, you'd be lucky to see one single event in total. Most of the time, you're just staring at your screens waiting for something that never happens.
So the prediction was silence.
Total silence.
And what did they get?
They saw 4 events.
4.
4.
Now, I know someone listening thinking 4. I have 4 pens on my desk. It's not a big number. But the context here is everything.
It's everything. Imagine you're an astronomer and you're told to look at a patch of sky that is completely, totally empty. And then you see 4 massive stars explode. The difference between an expected 0 and an observed 4 is it's astronomical.
I really liked how one of the researchers, Kosako Tobiaka, put it in the source. He said because the background noise, the chance of a mistake was so low, even seeing one event would have been striking.
Oh, absolutely. One event would have been, oh, wait a minute, let's check all the cables moment.
Right.
2 events would be, okay, we need to have a serious meeting moment. But 4 is so statistically unlikely under the current rules. You can't just dismiss it as a fluke.
So the traffic cop, the standard model, said, this road is closed, and 4 cars just blew past going 100 miles an hour.
And now we have to figure it out. Did the cars break the law, or is the law itself just wrong?
This gets us to the really exciting part, the explanations. If we assume the result is real, what does this mean? The source outlines 3 main theories, and they are, well, they're game changers.
They are. Each one implies the standard model is missing something, a big something.
Let's start with the first one. They call it heavy physics.
Right, so heavy physics is this idea that there are new, really massive particles out there that we haven't found yet, probably because our colliders just aren't powerful enough.
The giants hiding way up in the mountains where we can't climb.
That's a good way to think about it. And even if we can't see the giants directly, we might be able to, feel their footsteps. These heavy particles can influence lighter particles through these weird quantum interactions.
So what's the theory here?
The theory is that some unknown heavy particle is acting like an amplifier.
An amplifier?
Yeah. Imagine the normal decay is a really, really quiet radio signal. It's there, but it's too faint to hear. That's your 0.25 prediction. But this new heavy physics comes along and just cranks up the volume, making that decay happen way more often than it should.
So the decay itself is the same, but something invisible is just pushing more kaons down that specific path.
Precisely. It's reinforcing the signal. It would mean there's this whole other layer of heavy particles just beyond our view that are messing with the stuff we thought we understood.
Wow. Okay, that's huge. But the second theory, this one sounds even crazier to me. A new particle.
This is my favorite, just because it's so elegant. So the standard model says the kaon decays into a pion and 2 neutrinos. And we can't actually see the neutrinos, they're like ghosts. So we detect this decay by seeing what's called missing energy.
Right, it's like balancing a checkbook. You start with $100, you see a $50 charge for a pion, so you know the other 50 must have gone to neutrinos.
Exactly. But what if that missing $50 wasn't neutrinos? What if the kaon decayed into a pion and something else entirely?
Something we've never seen before.
A new, light, long-lived particle. Something that would also escape the detector, just like a neutrino. If that particle exists, then of course the standard model prediction was wrong. It didn't know that option was even on the menu.
So we thought the missing energy was one thing, because that's all we knew to look for. But it could have been this particle X sneaking out the back door.
And it fits the data perfectly. It just adds a new character to the cast of the universe.
Incredible. Okay, but there's a third option, a reinterpretation. What's that about?
This one is a bit more subtle. It suggests that what they saw wasn't a kaon decaying at all.
Wait, what? Then what was it?
Well, remember how these experiments work. You're shooting a beam of particles at a stationary target. You get all these violent collisions. The theory here is that those 4 events they saw weren't a kaon falling apart, but a new particle being produced in the initial collision.
So, born from the impact itself?
Yes, a new, light, long-lived particle produced at the fixed target. It then travels through the detector and does something that just happens to look exactly like the kaon decay they were searching for.
So it's a case of mistaken identity. We thought we were watching one thing die, but we were actually watching something totally new being born.
Which is, you could argue, even more exciting.
Yeah.
But in all 3 cases, the heavy physics, the new decay, the new production, the conclusion is the same. The standard model is incomplete.
All right. This all sounds a little too good to be true. And in science, if it sounds too good to be true,
it's usually noise.
Yeah. We have to play the skeptic here. Could this just be a mistake? A glitch?
It's the most important question, and the researchers are asking it constantly. We are working at the absolute limit of what our technology can do. We aren't taking photos of kaons. We're looking at, tiny electronic pulses in a detector. We're inferring reality from its shadows.
The source material used that exact analogy, measuring things by their shadows.
It's the perfect way to describe it. If you see a shadow on the wall that looks like a rabbit, it might be a rabbit. Huh. Or it could be your hands making a puppet. Or it could just be a weirdly shaped lamp. You're always dealing with secondary information.
And noise. in one of these experiments isn't just like static on a radio, what could it be?
Oh, anything. A stray cosmic ray from a supernova halfway across the galaxy, a random neutron bouncing off the concrete wall of the lab, even just thermal noise in the electronics. They spend years building shields and software to veto all that junk.
But they admit the data might be inconclusive because of this.
They do. They're being very, very careful. No one is popping champagne corks. The first job now is to go back and check all their assumptions about that background noise. Did they underestimate it?
But going back to what Torbayoka said earlier, even if it is noise, isn't that still weird?
And that's the beautiful catch-22 of this whole situation. Let's say it is noise. Let's say it's just some stray neutrons they didn't account for.
Okay.
Their prediction for the background noise was also incredibly low, essentially zero.
So they predicted almost no signal and also predicted almost no noise.
Exactly. So if it turns out to be noise, it means they fundamentally misunderstand their own experiment. It means their super quiet, shielded room is actually really loud, and they have no idea why. That's still a puzzle that needs solving.
So either way, something is broken. Either the standard model is broken or their understanding of their own detector is broken.
Yes. And that's what Torbayoka meant by even a single event is striking. Whether it's a real signal or just noise, something happened in that detector 4 times that absolutely should not have happened.
It really just shows you how fragile our understanding is at the edge of science. We build these gigantic, complex machines, and 4 tiny blips on a screen can throw everything we know into question.
That's the thrill of discovery. We call the standard model a fortress, but deep down, every physicist is secretly hoping to find a crack. Because that's where you learn something new. That's how you get to build the next better theory.
There's a playful name in the source for this potential new thing, right? The Decan.
The Decan, yeah.
Yeah.
It sounds like a comic book villain, but it's just this idea that there could be this whole new sector of physics hiding inside the Decan's behavior.
It just makes me wonder what else we're missing. I mean, if we're staring at shadows on a wall and we just barely caught these 4, what else is flying through the room that isn't even casting a shadow we can see?
That is the question that keeps the lights on at labs like CERN and J-Park. We know the standard model isn't complete, doesn't explain gravity, doesn't explain dark matter, doesn't explain why we're even here.
So these little anomalies, these weird kaon decays, they're the loose threads.
They are. And sometimes when you pull on a loose thread, the whole thing unravels, and you get to see the real pattern underneath.
So for everyone listening, the takeaway is this. We have this tiny, unstable particle. We watched it die. And it died in a way that seems to defy the laws of physics 4 times in a row.
And those 4 strange deaths might just be the birth of a whole new era in our understanding of the universe.
Or just a really, really noisy neutron.
Or a really noisy neutron.
Right.
But that's science for you. You have to chase the noise until it becomes a signal.
I love that. Chase the noise until it becomes a signal. That's a pretty good motto for just about anything.
It works for me.
Thanks so much for breaking all this down. It's complicated stuff, but I feel like I finally get why the number 4 can be so exciting.
Anytime. Always happy to count to 4.
And to our listeners, keep an eye on the shadows. You never know what you might find. We'll see you on the next deep dive.